So this is a spring mass system. This time a spring is not massless. Mass of a spring is given to you. So let us say, so let me read the question. This question says, and you form a spring of a spring constant K. So the spring constant K is given to you. Has a finite mass M. So mass of a spring is M. That is also given to you. Now question says, this spring is loaded with a finite mass capital M. If M is not negligible compared to M, so now question says M is not very small compared to M. So this also says M is not very small with respect to capital M. Are you getting? Now question says, so that the period of vertical oscillation is, so we have to find time period for the vertical oscillation. So this says T will be given as 2 pi under root M by 3 plus capital M, this divided by K. So in this case time period is given by this expression. So how will you proceed for this one? So let us think. So we will do this problem. So let us say at any point of time when a spring is, now we will do this question using the energy conservation principle. So let us say this time a spring has mass. This is not a massless spring. So let us say this is the natural spring you have. So this is the natural spring. Now at any point of time this spring is doing oscillation. So let me make, at any other point of time this spring is just stretched. Now let us say a spring is looks something like this when a spring is stretched by distance x. So this time the spring has a stretched by, so this is the natural length. Now this time a spring is stretched by x. So this is the x is the expansion in this case. Expansion of a spring is x, that is given to you. Now we are interested to, at this point of time this block is going with velocity v in the downward direction. So the capital mass M is going in the downward direction with velocity v. Now see, I am interested to find kinetic energy of block plus kinetic energy of a spring. Now this time basically a spring will also have some kinetic energy. Are you getting? Because a spring also has mass and the spring is also moving in the downward direction. So if you consider any mass of a spring, let us say this part. So if I consider this small part of a spring and let us say this is at a distance of x from the top, because I have already considered x, so it will be better to consider some different thing, or in case of x, so let us say call this as s, so that we don't have any confusion. So this distance is s. At a distance s, if I consider the displaced a small part, that is ds, now this spring and this portion of a spring is basically having some mass and it is also moving with some velocity, so it will have some kinetic energy. Now what is the mass of this part of a spring? You see the total mass of a spring is m and the length of a spring is L. So dm I can write, dm is basically equals to, for L is the mass is m, so m by L is the mass per unit length, that is lambda, into multiplied by ds, that will give you the mass dm. Are you getting? Let us say try to find what is the velocity we will have here. So since this spring is going in downward, this mass is going in the downward direction with velocity v, so all part of this spring must have velocity v. So velocity v is constant, so all part of a spring has to velocity v. Now velocity of each part will not be equal to v. If this velocity is v, and velocity of this part will be basically different. So let us try to find out. So this length is L. Now the lowest point basically has moved by a distance x. So I have assumed the displacement of a spring, the expansion of a spring is x. So I can say lowest point of a spring has basically moved by a distance x. So lowest point has moved by a distance x. If you see the top point, this has moved by a distance 0. So now you have two things. The lowest point, that is this point, lowest point has moved a distance x, and the highest point, it basically has moved a distance 0. You see here, this point is still here, it has not moved any distance. So now this means the expansion of a spring is not linear, not constant everywhere. Basically it's linear. So let us assume expansion of a spring is linear. So I am doing an assumption, and what is assumption is, so I am doing an assumption, elongation is linear. You can say elongation is linear. Elongation of a spring, elongation is linear. So this means if I have length of a spring is L, then at this point of time expansion is x. So at this distance when a spring has S, so if I have at a point that is placed at L distance, expansion is S. Are you getting? So if I will have a point at 1 unit length, so this is expansion is S by L. Or basically at L the expansion is x. So this is, so let me write again. So let us try to see. If I have length L, the elongation is x. If I have length 1, elongation is x by L. If I have length S, elongation will be x by L into S. Are you getting? So this is the elongation of a spring at a distance S. Are you getting? So I can write now elongation of a spring, and this is important. Elongation of a spring at distance x, at distance S, and this is equals to x by L into S, x by L into S. Are you getting? So elongation at distance S is given by, you can check when S is equals to 0, that is the point from here. So if you see, I am taking S from the top. If I take S equals to 0, elongation should be 0. So if I take S is equals to 0, and if we put this value x by L into 0, and this comes out to be 0, that is elongation is 0. Now you see, when S is equals to L, you must have elongation is x. So you see here. So when S is equals to L, this point, the elongation is x. So I will have, if I plug x by L and S is equals to L, elongation is x. So now basically this is a linear elongation. So what we have done is we have assumed elongation of a spring is linear. Are you getting? Now we will find, so this is the S, we will find velocity of a spring at distance S. So velocity of a spring, are you getting, at distance S, at distance S. So at distance S, what will be the velocity? Elongation is given by x by L into S. Are you getting? So I can differentiate this equation and I can get the velocity. So if I differentiate, so basically at S, so this means S is constant, so this is constant. So I find velocity, this is equals to, S is a constant, L is a constant, so S by L into dx by dt. And if I say dx by dt is V, so I will have S by L into V. So now find kinetic energy. So kinetic energy of elemental mass ds. elemental mass ds. So what will be the kinetic energy we will have? That is half times mv square, and mass is dm. So half times dmv square, so half times, and dm I have already calculated. You check your copy. So this is the value of dm, m by l into ds. So this is m by l into ds, and v I have already calculated, so s by l into v square. So this is the half mv square. Now if I integrate, so I will have half m l cube s square, v square is constant, and ds. So you will have s q by 3, and I have to integrate from 0 to l because the natural length of a spring is l. So I have to basically integrate this expression 1 by 2 mv square l cube s square 0 to l ds. So this will come out to be 1 by 3, so 1 by 6 mv square, and l square goes, so simply I will have mv square by l. So I think, any confusion? No, yes, simply mv square. So lq will goes. So this is mv square. So you check your copy. Now see, v is a constant, that's why I have taken outside of the integration, because v is dx by dt, rate by which the x changes at any point of time. That v is a constant v, it is not a function of s. Are you getting? ds by dt is basically changing, but the velocity v, that is dx by dt, is constant. Now let us find potential energy of a spring. That is easy. If you see, a spring has basically a stretched by a distance x, so I can have potential energy is half kx square. So potential energy is simply half kx square. Kinetic energy of bigger mass, capital mass, and this time this is again half mv square, and v is constant. Now if I write total energy of system when a spring has displaced by x, so now this is the total energy, is kinetic energy of a spring, kinetic energy of a spring plus potential energy of a spring plus kinetic energy of mass m, and this should be constant, because in this process there is no dissipative force that is acting, so energy has to be constant. So kinetic energy of a spring I have already calculated, so this is 1 by 6. Are you getting? So let us check. 1 by 6 mv square plus potential energy of a spring, that is simply half kx square. Kinetic energy of mass capital M is simply half mv square, and that is constant. Now we will follow the general procedure. If I differentiate this equation, let us cancel 2 throughout. So I will have, let us differentiate first, m by 6 to v, and differentiation of v is dv by dt plus half k to x, and then I will have dx by dt plus half m, v square is 2v, and then I will have dv by dt. This is equals to 0 because this size, all terms are constant. So let us say cancel these terms. So I will have m by 3 v dv by dt. So let me write m by 3, you can calculate yourself, m by 3 v dv by dt plus this 2 goes, so you have simply kx dx by dt plus, and this 2 goes, so m dv by dt. into v also, m dv by dt into v also. This is equals to 0. Now you see dx by dt is nothing but velocity. Dx by dt is v. Are you getting? At what rate at which this x is changing? So this x is so let us see here. So x is the total displacement of this point, end point. So this is the displacement of end point. So initial end point was here. So let us say it was here. And this is x that has been displaced. Are you getting? So mass is now here. Initially it was here. So dx by dt will give you velocity of this mass. So dx by dt is simply v. So I can replace dx by dt by v. And if I cancel v, so this goes, and this term goes. So velocity term goes. So I will have m by 3. And dv by dt can also be written as d2x by dt. So that dv by dt, let us take this common, m by 3 plus m. dv by dt, and this is equals to minus kx. So I can write dv by dt as d2x by dt square. This is equals to minus k by m plus m by 3 x. Are you getting? So from here you can find omega and you can find time period. So omega is under root k by m plus m by 3. Are you getting? Now if you see this equation, if a spring is massless, this m will be 0. In that case time period will be simply k by m. But now if the spring is not massless, you have to add mass, equivalent mass, that is m by 3. You don't have to add the whole mass of the spring. You have to add only m by 3 mass of the spring. Why this is so? This is because velocity of each part of the spring is not v. Velocity of each part of the spring is the lowest point of the spring will have velocity v, and upper part will have velocity 0, and in the middle it will lies between 0 and v, and that is basically linearly varying. This is the assumption I am making. If somebody makes assumption that the velocity variation is parabolic, he will not come across one m by 3 term. He will come something different. You can calculate yourself. If I say velocity variation is parabolic, and the lowest pull-up point has a velocity v and the top point has a velocity 0, because the topmost point has displaced by 0 distance, if the lowest point has displaced by x distance, because topmost point is fixed, in that case you have to write a parabolic variation. In that case you can find this m by 3 will be different. Are you getting? So this result I am getting is true only if assumption that is the variation of velocity is linear. Are you getting? Variation of velocity as well as variation of expansion, variation of elongation, that is linear. So what we have done, if you see this problem, only one important point we have, and the important point is variation of elongation throughout the length is linear. Lowest point will have elongation x. At a distance s from the top, elongation will be x by L into s. That is the elongation. And if I know the elongation at that point, I can get the velocity. If I differentiate the elongation, I will get the velocity. So that's why I am doing something like this. If you see here, this is the elongation. Elongation at s is x by L into s. And if I differentiate this term, I will get the velocity at distance s. For that point of time, s is fixed, because I want to find velocity at s. So I want what is the rate of change of x at s. So s is fixed, x is changing. So and that's why if I am differentiating, I am treating s as a constant. I am writing dx by dt as a v. Are you getting? And dx by dt is a v, and dx is something at the end point. This has displaced by distance x. So this dx by dt is v. That is basically constant for any time. If I consider for a particular time, this velocity is fixed. And that's why when I am doing integration, I am taking outside this velocity v square. I think all of you are able to understand this one. This is a quite good problem. You have to remember this result. When a spring is not massless, in that case, to find out the time period, I have to add a extra mass m by 3. So what is this? So if I have a system something like this, and now the mass of a spring is a small m and the mass of this is m, you can equivalently displace this system with something like this, and the mass of a spring is massless, and I have basically added a m by 3 equivalent mass. So I can basically represent this system ideally by this system, because the mass is m, that is already there, and I have added a m by 3 mass corresponding to this spring mass. So this is an equivalent system for this system. So this system is equivalent to this system. Let us finish it here and we'll discuss the next problem.